So now let's come to the different so-called regimes. So what does regime mean? Means different kind of different laws for different settings. The overall laws are the same, which are Maxwell's equations, but I can specialize them depending on the situation. So what are those special cases? So those are called different regimes. And so you notice one thing, let's start from the top. Maxwell's equations had a derivative in space and a derivative in time, right? They had terms like del cross E. When I open this, this is spatial derivative, right? I have terms like d by dx and so on. And they also had terms like time derivative. So there is a derivative in space and there is a derivative in time. And so the simplest thing you can do is to find out what is the relative weight of these two derivatives. If one is much bigger than the other, I can ignore the small one. If they are comparable, I must keep both of them. That is the basic idea. Okay. So the other thing about Maxwell's equations is that you would have again heard this in your undergraduate course on electromagnetics, is that you all heard the word boundary conditions, right? Some boundary conditions have to be satisfied by the field on the boundary, and we will look at those as we go. But again, what is the intuitive idea behind boundary condition is that if I have, let's say, an object over here, let's say size L, the electromagnetic field that is flowing around this object, it has to sort of respect this boundary. You know, it has to bend around it, twist around it. It can't behave as though it is not there, right? So let's, for example, let's take this direction to be x. So again, very intuitively, if I ask you that for an object of size L, how much do you think that this rate of change of the field along that coordinate x, what would it be? How would you write its relation with respect to L? If you didn't know, you don't need to know Maxwell's equation, this is intuitively. Should it depend, should it be proportional to L or inversely proportional to L? I am asking you rate of change of the field along x. What is your intuitive understanding? If you had two choices, proportional to L, proportional to 1 by L, what would you think? Proportional to 1 by L. Why? Because, so I say that this is proportional to 1 by L. Think of the case where L is very large, however, let us say even infinite. If it is very, very large, then there is no variation along the x direction. It is like the object is infinite. So the field does not have anything to bend around. L is so large. So d by dx, if I say 1 by L, 1 by L will tend to 0. That means there is no need for the field to change, because there is no change along that direction. On the other hand, if L was very small, then the field will have to sort of bend around it. So the smaller the field, smaller the object, the larger will be the bending of this field. Okay. So this is just intuitive, right? So we can say that d by dx is proportional to 1 by L. That's one side of the story, right? That's the space derivative. The other thing that we are looking at is time derivative. Okay. And all of you have done a course on something like signals and systems. So when I am looking at a linear system of equations, then what is the most convenient way of studying time or frequency? Fourier transform. Before that, represent everything in terms of a phasor, right? E to the j omega t. Once I understand the response of the system to e to the j omega t, I basically understand everything, right? So here I can take e to the j omega t. So when I take the time derivative of e to the j omega t, what do I get? So if I say d by dt, what should I get? Omega, j omega. So forget j is a constant, I am going to get omega. And omega in terms of wavelength is inversely, right? So this is going to be c by lambda, right? Forget all the constants, right? So all the action really is happening in the relation between these two terms. So I have a space derivative which is proportional to 1 by L. I have a time derivative which is proportional to 1 by lambda. Okay. So these are the two competing terms. Remember this, for example, this equation which I had, del cross E is equal to minus dB by dt. That was one of the equations, right? So it's like a tug of war between these two terms, and who is going to win, right? So based on the relative sort of ratio between L and lambda, there are these three regimes of physics that happen. So, for example, when let us say this L is much smaller than lambda, okay. So, that means what can I say? So, lambda is very large. If lambda is very large, what happens to this term? 1 by lambda will become very small, right. So, I can ignore the time part of these Maxwell's equations, right. So, this part is going to become very small and this part will dominate, right. So, if there is no time dependence, what are those kinds of equations called? We have studied it in school. Differential equations, but a little bit more special name for it, statics, right. Because there is no time dependence, we call them electrostatics, magnetostatics or whatever. In general, you will just call them statics. And if I do not have the time terms, then I have the space derivative of electric field, space derivative of magnetic field, and there is no coupling between them, because the coupling was happening via time derivative. So, these statics, they are uncoupled system of equations. Electric field has its own story, magnetic field has its own story, okay. So, we call them, that is why you have heard the words electrostatics and magnetostatics, right. You do not hear electromagnetostatics, right. So, these are uncoupled. Alright, then comes the case obviously where these two derivative terms are comparable, right. So, that is what is called the mid frequency, okay. So, in this mid frequency range there is no escape, I have to use both the space derivative and the time derivative, okay. You can imagine that statics would have been easier because there is one term less. Mid frequency is the most difficult situation to handle because I have to take care of both these derivatives, okay. And most of I mean this course will be focused mostly on the difficult part, which is mid frequency range, okay. So, that is, so here you get coupled equations, okay. Another thing is that when these equations are coupled, as you saw in the slides before when I showed you Maxwell's equations, when I have coupled equations, the equation of a wave comes out. So, the mid frequency range has wave like solutions, okay. So, that is again something we will see. So, they are like wave like, and that is how you are able, your cell phone is able to send a signal to the base station and we are getting light from the sun, because these are all waves, waves can travel. On the other hand, if you look at the solutions in statics, they are not wave like, they are smooth solutions, no, Laplace equation, Poisson's equation, they are not wave like, they are smooth. So, they are short range, okay, relative to at least the mid frequency range. And finally, the third regime is where the object size is much larger than the wavelength. So, can anyone tell me where you have seen such a situation arise? It is very common. Light, right. So, in light, for example, the light with which we are seeing right now, the wavelength is how much? 500 nanometers, let us say. What is the size of our day to day objects? On the order of centimeters, meters, right. We can't see much less than, I mean micron also we need a microscope, right. So, there the wavelength is much smaller. So, the object, I mean the field need not vary or change dramatically around an object because the object size is so large. So, what happens over here is you get, this is the regime of optics and you get ray like solutions, right. Okay. So, we will be focusing in this course mostly on the mid frequency range. For both the statics case and the ray optics case, there is a specialized theory which makes use of this assumption. So, if you use these two assumptions, you can simplify your mathematics a little bit more. You do not have to use all the heavyweight machinery that mid frequency needs, okay. On the other hand, if you understand mid frequency methods, it is much easier for you to understand the other methods because they are simpler versions, right. So, we will focus on this the mid frequency methods in this course, okay. Any questions so far? Okay, should be fairly clear till now.